Okay, so let's have you try this scalar line integral. Here we're just evaluating y ds, where c is the line segment between these points. So go ahead and put this on pause and see what you can come up with. All right, so I'm going to just zoom in on the answer here because we actually have lots of different ways we can get this answer. I'm going to show 3 different common ways you'll see this. And what's changing in each of these is the way that I choose to parameterize the curve. So this first parameterization option is saying I'm starting at the point 1, 3, and I'm moving to the point 3, 7. So I'm going to do 1, 3 plus how far I'm moving in the x and y. And when I do it that way, my t is just going from 0 to 1. And you'll notice in that case that when I go change variables and evaluate, I end up with 10 square root of 5. Now, option B is instead of parameterizing starting at 1, 3, ending at 3, 7, instead of t going from 0 to 1, I could actually come up with this line like y equals mx plus b, and then parameterize by letting x be t, and then y would be 2t plus 1. And if we do that, your x is t, so t is now going to be going from 1 to 3. You'll have a slower speed, square root of 5, but you notice we get the same answer at the end. And then lastly is I could have started at, I didn't tell us which direction, and I could have started up here at the point 3, 7 and gone the other way. And even in that case, I still end up with the same answer. So this is important because we can go back to what we had asked on the previous slide here that said if we change the direction of the curve or if we use a different parameterization, will the line integral of a scalar function change? And the answer is no. We just saw that specifically with this example. Now, if we change the path between 2 points, for example, if I start here and then I end here versus doing this, then yes, the answer will change. And you can think of it as, for example, if I wanted to find the mass of this wire versus the mass of this wire, even though they're starting and ending at the same points, I'm integrating over a longer curve over here in C2, let alone I haven't even thought about how my density might be changing on these curves. So I don't expect them to be the same, even if they just start and end at the same points. Okay, let's go back and do one more example. And again, I'm going to have you put it on pause. And now we're going to have a particle that's moving in the xy plane. The temperature in the plane is varying, and we'd like to know what's the average temperature on the particle's path. So think about how we've defined average values so far when we were looking at, for example, double integrals or triple integrals. And now think, how would I define an average value over a curve, for example, for a scalar line integral? So go ahead and put it on pause, see what you can come up with. Okay, so I'm going to walk us through this answer as well. And the first thing to start with is that to define average value, we're going to do similar to what we did before, where you're going to integrate whatever you're trying to find the average of. And then you're going to divide by, in this case, it's just going to be the length of the curve. When we were doing this with double integrals, it was the area of the region. When it was a triple integrals, it was volume. But in this case, you're just integrating the line integral with just ds. Now, there's more than one way to parameterize this curve, but an easy way, since it's given to us as a function of x, is to just let x be t, and then y becomes 2/3 t to the 3/2, and t is 3 to 8. And that's how I can end up pulling out my speed here. And so notice in this case, we're going to do both pieces. Here I'm starting with the denominator. I'm just trying to find the arc length. So I'm just integrating the speed dt, and that's going to end up giving me an arc length of 38/3. And then secondly, I'm going to now integrate the temperature. So I need to change the temperature in terms of, so here's temperature. I need to rewrite y squared. So that's what I'm doing here. There's y squared. And then times the square root of 1 plus x is right there. And then here again is my speed dt. which is another way of writing my ds. And when I combine all those things, I get, it's a crazy number, but I get this fraction here. And so at the end of the day, because I want the average, I'm going to take the quantity I had here divided by this, and it's going to give me an average temperature of 263 degrees approximately along this path.